as if you did the homework on this bicycle problem. So if you want to jot them down on the side, then we're going to move on with some torque problems. If you didn't solve them yet, just write down the answers. Then, let's see. And there's more than one way to solve all of these. Okay, now, we are on torque. Previously, we did Newton's second law, F equals ma. But it always gets described like this. The acceleration is always directly proportional to the force and inversely proportional to the mass, right? Now, for torque, the resultant torque applied to a rigid body will always result in an angular acceleration that is directly proportional to the applied torque. Think of this as force, but this is really the torque. Think of that as force and inversely proportional to the body's moment of inertia. This is the moment of inertia. Think of that as being equivalent to the mass. Then it should look the same. This, of course, would be in radians per second squared. So instead of F equals ma, we simply have here torque equals I alpha. Torque equals the rotational equivalent of mass alpha. Now this I is the moment of inertia, is the most interesting thing. It is rotational equivalent of mass. And it varies depending upon the shape of the object and where the rotation is. So if we go to the next page, I'm not worried about anything else on this page. If we go to the next page, we will see that. Probably you may know that a large diameter wheel has a greater rotational inertia. Now this is just like, Newton's law of inertia. Object in motion wants to stay in motion, object at rest wants to stay at rest. So we have the same thing, but if you get a large diameter wheel has greater inertia than an equal mass wheel of smaller diameter. So what is the moment of inertia squared of simple objects like this one? If we had something like this where we know that this mass is rotating about this axis. If this is rotating right here, then and this is centered, then we know that this is 2 meters this way. 2 meters this way. So if we sum this up, this moment of inertia, if this is spinning that way, would be m1 r1 squared plus m2 r2 squared. It's a summation of all of that. And I duplicated this twice for some goofy reason. So the moment of inertia here, you'd have 5 kilograms times 2 squared plus 7 kilograms times 2 squared. You have 20 plus 28, we get 48 kilogram times meter squared. But let's look at the chart on the next page. On the very next page, this is where you have to look at your moment of inertias. You got a hoop here, central axis, it is just mr squared. You have a solid cylinder or disc about the cylindrical axis here. This is 1/2 mr squared. That would be the same as 1/2 mr squared. All right, you'll probably see it this way. Thin rod about the axis through the center. ml squared over 12. They have a solid sphere about the diameter. So this is not spinning on a central axis. So you could have a hoop going this way. That's just a goofy one. You have a solid cylinder about the central diameter and a thin rod about one end on the axis and a spherical shell and so on. It would have to state the shape for you to calculate these. So let's go back. We looked at that for a second. Let's go back to one more thing. So now we are going to have, we have this equation first. Omega final squared equals omega initial squared plus 2 alpha theta. This is v squared, v final squared equals v initial squared plus 2ax previously. But in rotation we would have it this way. If we do some substituting, we can show, and I'm not going to go through the whole thing, that rotational kinetic energy, instead of 1/2 mv squared, right? Previously we did kinetic energy this. If it's rotating, 1/2 I is the rotational equivalent of mass, and omega is the rotational velocity, right? So you have rotational kinetic energy. It looks the same. Again, your moment of inertia is your rotational equivalent of mass, I. Okay? So 10-9 helicopter blades. Let me see if I can find that real quick if I have this open. I'm going to come back to this. 10.9. If I do a Control F, will get me right there. Control F, 10.9. That's not going to work very well. Helicopter blades like this, 4 meters long. And then next we'll calculate moving rotational energy down an incline. So we got 4 helicopter blades. Calculating helicopter, a typical small rescue helicopter similar to the one in figure 1018. 4 blades, 4 meters long. We got a mass of 50 kilograms. The blades can be approximated as thin rods that rotate about one end of the axis. So a thin rod rotating at one end of the axis, what do we get for a moment of inertia formula? And you saw the blades. Thin rod. Yes. The rotational moment of inertia would be figured with ml squared over 3. The helicopter has a total loaded mass of 1,000 kilograms. Calculate the rotational kinetic energy of the blades. So for A, for rotational kinetic energy, we are going to be looking at, instead of 1/2 mv squared, 1/2 I omega squared. Well, let's do I first. We want total, there's 4 blades. And then we want to use ml squared over 3. So this is my 4 blades. It doesn't matter how I do this, will be fine. My mass of my blades, 50 kilograms. Length of my blades is 4 meters. My total rotational moment of inertia yes, I'm missing my squared. But 1,067 should be right. So that's my I. What is my omega? If this thing is going 300 RPMs, we'll change 300 RPMs to, what units do I need here? Radians per second. So omega is going to equal to 300 and then we are going to go 1 revolution, 2 pi radians. 31.4. There's my 1/2 I omega squared. $526,000 joules. Okay. We're going to skip B. The translational kinetic energy is going to be 1/2 mv squared. We're going to do C. To what height could the helicopter be raised if all the rotational kinetic energy could be used to lift it? So you're applying, we'll set this equal to mgh. So our rotational kinetic energy equal to mgh. And we're looking for height. So it would be our rotational kinetic energy divided by mg should be our h, right? So at 526,000 joules, mass of that helicopter is 1,000 kilograms, 9.8. What do we get? 53.7 meters. So a guy spent how many months in a barrel, made it across the ocean? I keep thinking rotation and barrels. Anybody been in Niagara Falls? Have you ever seen the documentaries of people climbing into a barrel and going over Niagara Falls? Like one guy strapped himself to a chair. Like, how could that be a good idea? You know, some. But yeah, this guy. Let me see if I can find it real quick. Barrel ocean crossing. Where's the dang thing? Oh, yeah, BBC. Ah, that's all he's going to show? Oh, there it is. Yeah, he was in this thing for months. Took him an extra month, too, but I guess he made it. He's a Frenchman. What's that? Just he used the ocean currents, yep. Yep. I keep thinking you see stuff like this, like Don't these people ever have to have a job? You know, how many people have enough money to just do, oh, what are you going to do? Well, I'm just going to spend my life trying to make it across the ocean in a barrel. Well, I guess that would work. Now here's a question for you. If we just roll something down an incline, let's just take a bowling ball. And we're going to roll it into you. Heck, let's do a boulder then. That thing has two types of energies that's going to hit you. First of all, if the thing's rolling, right, it's got some rotational motion to it, and it has some translational motion to it, right? So if something is rolling down an incline, there are two motions to that thing. So we're going to calculate, and it matters what the shape is. So calculate the speed of a cylinder rolling down an incline. Calculate the final speed of a solid cylinder that rolls 2 meters down a 2-meter high incline. The cylinder starts from rest and has this mass and radius. So we have a cylinder, 2-meter high incline. Solid cylinder. I can't draw it the way I just did, but so, and by the way, it would get to the bottom with the fastest speed if it just went without friction and never rolled. But this thing is going to start rolling, right? It's going to have two energies at the bottom. It's going to have translational, moving in a straight line, and it's going to have rotation. So here's what we're going to have. We're going to have potential energy at the top is going to equal to kinetic energy, regular translational kinetic energy, plus rotational kinetic energy. It only starts up here with potential energy. So to develop this, we would have mgh, right? Just mgh. Starts from rest. It only has mgh on top. We've done this before, translational. 1/2 mv squared. But rotational is going to be plus 1/2 I omega squared. We have a solid cylinder. So if we have a solid cylinder, there's our solid cylinder. So our moment of inertia is one half mr squared. And then omega will substitute in. How do we get between angular velocity and translational velocity? So this, we know that if we take our radius times our angular velocity, we get our translational. So we're going to substitute that in there. So what is omega is V over R, right? Omega is V over R. So we're going to substitute in V over R right there. So let's take this all down here. We have MGH equals 1/2 mv squared plus inertia is 1/2 mr squared and my rotational velocity is going to be V over R, but I still got to square that, right? So I can go V squared over R squared. What can I get rid of? Get rid of M. What else can I simplify this? I can get rid of this R squared here, right? So if I clean this up now, I have GH equals 1/2 V squared plus 1/4 V squared. Mass is gone. Because I got to solve that for V. We're going to solve that for V. And we don't have it on this side. So 1/2 plus 1/4 is going to be 3/4. So we have GH equals 3/4 V squared. And if we solve this for V, we'd end up with 4GH over 3 square root, wouldn't we? No, I don't think. Well, we have to add the 1/4, a half. This is 2/4 and 1/4 is 3/4. So multiply both sides by the reciprocal, 4/3. I think we're going to end up with 4GH divided by 3, right? So if we plug this in, we're going to end up at 5.11 meters per second. Right here. So we have omega squared, but we're going to substitute V over R for omega, and then we still have to square it. All right, let's do some torque. If something's in equilibrium, we say up equals down in the Y, and we say left equals right in the X, correct? So the first condition necessary to achieve equilibrium is already mentioned, up equals down, left equals right, essentially. The second condition necessary to achieve equilibrium involves avoiding accelerated rotation. So torque is the rotational equivalent of force. So if you are applying a torque, you are now doing some kind of rotation on something. So torque has this T tau symbol like this. It's the radius force times sine theta. Well, typically you think of like something like this. If you apply a force up here of 10 pounds, and this is 1 foot, your torque is the radius 1 foot times the force of 10 pounds sine theta. If you are doing it like this, it would be the sine of 90, and the sine of 90 is 1. This is 10 foot-pounds, right? If you need more torque, and you have a broken arm, so you can only do 10 pounds of fixed force, what do you have to do to get more torque? You need a longer wrench. You need to put a pipe on it. You need to clip a wrench to a wrench and all that stuff. Cheater bar, all that stuff, and get somebody to stand on it and break crap and everything else. In the take-home quiz, the Ferrari Testarossa has 1 nut. And the question I made, the damn bar is 6 feet long, I believe. It's 325 foot-pounds of torque. So if you're going to do 325 foot-pounds of torque, you probably need a long bar, but you only have 1 freaking nut holding the entire wheel on, so you probably want to do that. So if this is 90 degrees, it is simply that. It's that simple. It's the radius times the force. But if you start doing a goofy angle on this, then we've got something else. So positive torque counterclockwise, negative torque clockwise. It's kind of the general rule. This just explains the next page. So let's go to the next page. So we just look at this and say, how does A, B, and how does B through F compare to A? So I'm going to say this force right here is 10 newtons. Now let's make this radius starting out 1 meter. So this is looking at a door from overhead. Are we going clockwise or counterclockwise? We're going counterclockwise. Is that positive or negative? Okay. So this is positive torque equal to 10 newton meters, right? Now, B just says you reduce the force to 5 newtons. So if you keep the same radius and you reduce the torque, or excuse me, force to 5 newtons, your torque now is 5 newton meters, right? They're just saying you reduce the force. Now in C, we kept the same force, We'll make it 10 newtons, but they reduce the radius. So if we call that 0.5 meters, we can still have a positive torque of 5 newton meters, right? The only difference in D is they're just applying this in the opposite direction. So this is going to be negative torque, 10 newton meters. Now, everything here, the angle's been 90 degrees, right? Now we're doing here at a different angle. So now we draw an action line from our force to where it intersects our pivot point. So now we have an angle, we are less than 90. So now we would have to actually use r sine theta for this. This right here is not applying any torque. This is not going to cause any rotation, right? If you're pulling on the door straight out, that's not going to cause any rotation. You know, and you could say that the force is applied at 0, huh? Now here's where, right? And then you learned if one of them jumped off and slammed the other butt, you know. They have teeter-totters yet? Or are they too dangerous now? I think they still have them. Some do, some don't. Catapults sometimes. Or you get slivers in your butt. Now, you apply the two conditions of equilibrium. Up equals down. Clockwise torque equals counterclockwise torque. So, oh, I don't have time to throw that up there. Let's do this. So first of all, I'm just going to do condition 2 for rotation. Clockwise torque equals counterclockwise. Which mass is going to cause this to spin clockwise? Mass 2. That's going to be a force of weight. The distance they are from the pivot point is R2, correct? So I'm going to put my G in here right now as a force. This is going to be M2G R2, whatever they are from the pivot point. If they are balanced and it is not moving, then counterclockwise, right, and you can see it this way, is going to be M1G R1, right? If they are balanced, trying to go counterclockwise should be equal. So let's see, M2G, we can cross out G, and the first child, M1, is 26. Do we know what it sits 1.60 meters? The second child has a mass of 32 kilograms. Where would they sit to balance that? What, he's get 1.3 meters? Now, I'll do one more problem, and that's pretty much going to finish this up. We're going to look at this pole vault problem right here. Oh, I was there. Oops. 326. Hold on to the pole vault. Center of gravity of the pole vault right here. Whatever the force of weight is of the pole vault would be distributed equally by force up of the right hand and force up of the left hand, correct? But as soon as you move away a little bit, this right hand would hold more up than the left hand. But then we have this. So this is what it might look like before the pole vaulter starts running, to where left hand's going to apply the upward force. Force of weight down here, isn't this one going to stop it from rotating? So I want to do this problem here to finish us off. And then this will pretty much, I'll be happy. So I'm just going to draw this out of what this looks like. So this is page 326. It looks like this. This is the center of gravity of that pole. It's the force of weight down, mg. It is 49 newtons. Force of the left hand up. Force of the right hand down. This is 0.6 meters. And this is 0.9 meters in here. Now, you can pick a point of rotation, because if you pick a point of rotation, that is where a force is, then the distance is 0. So we're going to rotate at the left hand. And then we'll say the torque clockwise will equal the torque counterclockwise. What's going to make it, so we're rotating right here. Again, you can pick whatever point you want to rotate, but we need to find these forces. So we'll rotate it right there, and then we eliminate that. So making it rotate right there clockwise is going to be this weight times this distance, right? This is going to be 49 newtons. It's 0.6 meters away. The force of the right hand We do not know. And that's 0.9 meters away. So if we solve this, it's 32.7 newtons. Now your book has this wrong for the next solution. I'm going to do one more thing next time we meet. All I'm going to do is change the rotation to here. I'm going to calculate the force of the left hand. Print out that quiz, work on that. So when we meet Tuesday, if you're listening to this recording, you're in Monday class, I mean Monday, or excuse me, this would be actually on Tuesday, no matter what. When we meet Tuesday, we'll go over questions on that, bubble that thing in. And I changed the question today. So if you printed it before today, cut and paste, just look at it. It's a really simple question on a torque like this. So I did change, you'll see the diagram right away.